All right, let's talk about vectors. We're going to go way beyond just the formulas and really uncover the intuitive, geometric meaning behind the math. You know, the hidden language that's used to build pretty much everything from bridges to video games.
So we all learn in school that adding vectors is pretty easy, right? You just place them tip to tail. But in the real world, for physicists and engineers, you're usually faced with this messy jumble of forces that isn't nearly so straightforward.
Okay, let's dive into this with a really classic problem. I mean, this is something every engineering student runs into. Trying to calculate the total combined force from a bunch of different vectors all acting on a single point. Now, the challenge here isn't just adding up some arrows on a page. It's about taking all these different forces, and each one has its own unique strength and direction, and somehow boiling them all down into one single final vector that tells you the whole story.
The standard way to do this, as you can see here, is to break each vector down into its basic x and y parts. And look, it seems simple enough, but according to engineering professor Dr. Brian Bernard, this is exactly where things go wrong. Students make critical mistakes right here, mostly because they're just following a recipe without really having that deeper geometric intuition.
So, if we want to avoid those traps when we're breaking vectors down, we first have to understand how vectors actually relate to each other. And that relationship, well, it's revealed through multiplication. But here's the twist. With vectors, there isn't just one way to multiply. There are two. I mean, really think about that for a second. If you're multiplying two things that both have direction, what question are you even trying to answer? Well, it turns out there are two incredibly powerful and logical ways to do it, and each one tells you something completely different about how those two vectors are related. So the first method, that's the dot product. It basically answers the question, how much are these vectors aligned? The second one, the cross product, answers, how perpendicular are these vectors? One gives you a single number that represents their similarity, and the other gives you a brand new vector that represents their difference. Okay, let's really get into that first type of multiplication, the dot product. This one is all about alignment, all about similarity.
And this slide, I think, just captures a beautiful analogy from a Reddit user over on r/AskPhysics. They said the best way to picture the dot product is to imagine a light source shining straight down on one vector, casting a shadow onto the line of the other one.
The length of that shadow, which by the way is determined by the cosine of the angle between them, multiplied by the length of the vector it's falling on, that right there gives you the dot product. So if they're perpendicular, the shadow has zero length, and the dot product is zero. Makes sense, right? And if they're parallel, you get the biggest possible shadow.
And this is where the magic really happens. That intuitive geometric idea of a shadow, it translates perfectly into a ridiculously simple calculation. Algebraically, you just multiply the matching components of the vectors and add up the results. Two totally different ways of looking at it, but you get one single answer.
So why do we care? Well, this one simple operation answers some really crucial questions. In physics, it tells us how much work is actually being done by measuring the force that's applied in the direction of motion. And in computer graphics, it answers how bright should this surface be lit by measuring how aligned a light ray is with that surface.
All right, let's switch gears to the second type of multiplication, the cross product, and you'll see how this builds a completely different idea. If the dot product is about being parallel, the cross product is all about being different.
So instead of a shadow, the cross product asks a different question. What's the area of the plane that these two vectors define? The more perpendicular they are, the bigger the area of that parallelogram they create. And if they're parallel, well, they don't form a parallelogram at all, so the cross product is zero.
Now, the result of a cross product isn't just a number. It's a whole new vector. And the direction of that new vector is always perpendicular to the plane that the first two vectors created. We figure out its direction using the good old right-hand rule.
This is absolutely essential in 3D graphics for finding what's called the normal vector, basically the direction a surface is facing, which tells a game engine how light should bounce off it. And in physics, it's the foundation for literally anything that rotates, letting us calculate things like torque, the twisting force you use on a wrench.
So here's the crucial point. With this deeper, geometric understanding of how vectors actually relate to each other, we can now go back to our original problem and see exactly how to sidestep those common traps.
According to Dr. Bernard, students who are trying to break down vectors into their components consistently fall for three major mistakes. And these aren't just random errors. They almost always come from memorizing formulas instead of actually visualizing the geometry. The first mistake is just blindly memorizing x's cosine. It's not. It totally depends on which angle you're given. The solution is so simple. Don't memorize. Just draw the right triangle for each vector and see for yourself which side is adjacent, that's cosine, and which one is opposite, that's sine.
Dr. Bernard actually calls this mistake the most serious one because it really shows a misunderstanding of what sine and cosine even are. You have to remember, cosine is just a ratio. It's adjacent over hypotenuse. The fraction 12 over 13 is the cosine value. So plugging that fraction back into the cosine function on your calculator is like asking what's the cosine of the cosine. It's a completely meaningless question. You either use the fraction or you use the angle with cosine, but you never ever use both.
And finally, trust your drawing more than you trust your calculator. Your calculator has no idea about the visual context of your problem. If you've drawn components that are pointing up and to the left, you know the answer has to be somewhere between 90 and 180 degrees. If your calculator spits out a negative number, yeah, it's a mathematically related answer, but it's not the one in the quadrant you're actually looking at. A quick sketch will save you from this trap every single time.
So after all that, let's bring these really powerful ideas together and see how they really are the building blocks we use to describe our physical world. From simply adding forces together, to figuring out the alignment of light with the dot product, to finding the axis of rotation with the cross product, these are not just abstract math problems. They are the fundamental tools we use to model, predict, and manipulate the world around us.
Ultimately, understanding the why behind the formula, the shadow of the dot product, the area of the cross product, it does way more than just help you get the right answer on a test. It reveals this elegant, intuitive geometry that's hidden inside the math that builds our world. The only question is, what other geometric truths are out there, just hiding in plain sight?